Okay, chemistry kids, today we are going to be continuing our discussion on 2-5. So, visible learning objective 2-5 is all about nuclear chemistry. And we had a lesson just a little bit while ago just talking about types of radiation and radioactive decay. And now we're going to be talking about a property called half-life, which has to do with the natural radioactive decay of different radioactive isotopes. So we're just going to finish up the last part of 2-5, which corresponds to this concept of half-life. And I want to show you, just outline what the concept is basically, and show you the kinds of problems that you're going to have to be able to answer when it comes to half-life. It's pretty simple. It's pretty straightforward. We're not going to be doing anything too difficult with the half-life concept in this course, but it can be a little bit more tricky than what we present. But right now we just want to know the basics. So let's go to the visible learning document. I'll pull it up and let's go to 2-5 and let's look at the part. Whoops. Whoops, I'm not doing the right thing here. Hold on. Okay. So in 2-5, we've already talked about 1 through 8, and now we're going to talk about half-life. Okay. So the different calculations we have to do, and kind of the different ways to interpret it. Percent remaining versus the percent of the sample that is remains after a certain amount of time versus the percent of the sample that has decayed, or the fraction that remains versus the fraction that decayed. And we want to be able to, given a half-life graph, be able to determine the value of a half-life. And so just those are the basics, and those are what we're going to be covering today in today's lesson. So let's check it out. So half-life is an intensive property, and basically what it is the amount of time it takes for the radioactive isotope to cut in half, the mass of that radioactive isotope to cut in half. Okay, so the amount of time required for the quantity to fall to half of its original value. So let's say I have 5 grams of carbon-14. The amount of time it takes for that 5 grams to decay down to 2.5 grams of carbon-14, that's what we're talking about. Whatever that amount of time is, that's the half-life. Okay. So carbon-14 has a half-life of 5,730 years. What does that mean? It means it takes a sample of carbon-14 5,730 years to cut in half. So if you have 100 grams, it would take 5,730 years for that 100 grams to cut in half to 50 grams. Okay? And then it would take another 5,730 years for that 50 grams to cut in half to 25 grams, and so on and so on. The amount of time it takes for the sample to cut in half does not change. It's an intensive property for that isotope. So if it takes 5,000 years for 100 to go to 50, it would also take the same amount of time, 5,000 years, for 1,000 to go to 500. Doesn't matter how much you have, for it to cut in half always takes the same amount of time. And that amount of time, the amount of time it takes for the sample to cut in half once, that is what a half-life is. And it's marked by this notation here. T1 half is the amount of time it takes the sample to half itself. Okay? So again, you could start with a 500 gram sample of carbon-14. Okay? After 5,730 years, that 500 gram sample of carbon-14 is now going to be 250 grams of carbon-14. And even if you just started with 10 grams, if you had 10 grams of carbon-14, it's going to take the same amount of time to go from 10 grams to 5 grams as it does to go from 500 grams to 250. Same amount of time. Okay? Half-life stays consistent with that radioactive isotope. Okay? So a lot of times we can think of half-life as a fraction. Okay? you can think about this. After every half-life, your sample gets cut in half, but another way to think about that is the sample gets multiplied by 1/2, right? Dividing by 2 is the same thing as multiplying by 1/2, okay? So if your sample decays for 2 half-lives, you're going to cut it in half twice, which means you're going to multiply by 1/2 twice. Well, 1/2 times 1/2 is 1/4. So what does that mean? It means if you have 2 half-lives, if your sample cuts in half twice, you're going to have 1/4 of what you originally started with. How did I get 1/4? 1/2 times 1/2. Okay. If your sample undergoes 4 half-lives, then you're going to multiply by 1/2 times 1/2 times 1/2 times 1/2. That comes out to be 1/16. Okay. So if your sample undergoes 4 half-lives, what's going to be the amount of sample that remains? 1/16. Okay. If your sample undergoes 3 half-lives, what fraction is going to remain? That would be 1 half-life times 1 half-life times 1 half-life. That would be 1/8 remains. Okay. So here's a sample. 20-gram sample of carbon 14 sits for 11,460 years. What mass remains? So the first thing is to figure out how many half-lives have occurred. So one way to do that is take the total amount of time and divide by the value of half-life. So remember, the half-life of carbon-14 is 5,730 years. So if I take my total time here and I divide it by 5,730 years, that's going to give me 2 half-lives, or 2 times the sample cuts in half. So one way to go about that is just, in your head, you could do 20 divided by 2, that's 1 half-life. And so after you divide 20 by 2 once, you have 10, and then 10 divided by 2 is 5. So the answer is 5 grams remains. But the one way to do that is 20 times 1/2 times 1/2, or 20 times 1/4. So 1/4 of the original amount remains, and in this example, that would be 5 grams remains. Okay? Okay. A radioactive isotope has a half-life of 55 seconds, so T1/2 equals 55 seconds. What fraction of the sample will remain after 275 seconds? So what we'll do is we'll take our total time and we'll divide it by the value of a half-life. So we'll take 275 and divide it by 55. And so that means 5 half-lives occur. So that means the sample cuts in half 5 times. Okay? Now, another way to say that is it gets multiplied by 1/2 5 times. Well, 1/2 raised to the 5th power, right? 1/2 times 1/2 times 1/2 times 1/2 times 1/2 is 1/32. So what you can do is that's the fraction that's going to remain. So the fraction that remains after 5 half-lives would be 1/32. Okay? So here, after this number of half-lives have occurred, this is the fraction that remains of your original sample. So 0 half-lives, you have 100%, right? 1/1. After 1 half-life, 1/2 remains. After 2 half-lives, 1/4. After 3 half-lives, 1/8. After 4 half-lives, 1/16. After 5 half-lives, 1/32. After 6, 1/64, and so on and so on and so on. Okay, so I think you get the idea. Okay. Right. You might also want to think of what percentage that remains or decays as in terms of percentage as opposed to a fraction. So after 0 half-lives, you still have 100% of your original sample. But after 1 half-life, you have 50%. After 2 half-lives, 25. After 3, 12.5. And notice that if we start at 100%, after every half-life, we've divided by 2. So divided by 2 is 50. 50 divided by 2, 25. 25 divided by 2, 12.5. 12.5 divided by 2, 6.25, and so on and so on. Okay. Now, if you were to graph the way this looks, you're going to get a curve that looks like this. Okay. So here's a curve, and it's kind of hard to see the numbers, but let's talk about it. All right. So this is the amount of time, and this is the number of the atoms. So number of atoms would be directly proportional to the mass. So the number of atoms of those radioactive isotopes. So if you can find where it cuts in half and go down here, like, so if you know this number right here, what you're starting with, right, and you take half of that, okay? So again, it's kind of hard to see here, but this looks like we're at 1 million, okay? 1 million atoms right here, okay? I think, or 100,000, sorry. This is 100,000, and then half of that is 50,000. So if we go 100,000 to 50,000, we go over here. So this is the amount of time it took to cut in half. So almost 4 days. All right. Let's see if we have a better graph here. Okay, here we go. Here's 100,000. Here's 50,000. Or sorry, 10,000 and 5,000. Sorry. So you started with 10,000. Half of that is 5,000, and the amount of time it took to go from there to there was around 360 seconds. Okay, and then from 5,000 to 2,500, it should take about the same amount of time. Okay, it should take the same amount of time. Let's see if we have another graph that shows it a little bit more. All right, so to go from 1,000 to 500, that's the first half-life. From 500 to 250, notice it's the same amount of time. That's 2 half-lives, right? 250 to 125, that's 3 half-lives, but again, the same amount of time to go from here to here, same amount of time as it took to go from here to here, and then the same amount of time to go from here to here. So notice the time it takes for the sample to cut in half doesn't change. Okay, so this would be after 1 half-life, after 2, after 3, after 4, and so on. Okay. All right. So let's look at another practice problem, right? A sample of organic tissue that contains carbon is analyzed, and it is found that 12.5% of the carbon-14 remained. Remember, carbon-14 has a half-life of 5,730 years. So we want to know how old the sample is. So how long did it take for 100% of carbon-14 to go to 12.5%? Well, if you start with 100%, divide it by 2 is 50, divide that by 2 is 25, divide that by 2 is 12.5. So how many times did the sample cut in half? It cut in half 3 times. So that means 3 half-lives have occurred. And if 1 half-life is worth 5,730 years, all you have to do is multiply that by 3, and that is approximately how old our sample is. Okay? So there's a bunch of practice problems you can do, but what I will say is you're not going to have to deal with logarithms in this class. So you're always going to have whole number of half-lives. So if the half-life is 10 days, then I might ask you how much remains after 10 days, or after 20 days, or after 30 days, or after 40 days. It will always be a whole number of half-lives that take place, right? If the half-life is 10 days, I won't ask you how much is going to be remain after 12 days. It's not going to be fractional half-lives. So you don't have to worry about problems like that. So let me show you a couple problems that you might have to answer, and then I'll show you something that might help. All right, so here's some half-life problems, and this is posted in Schoology, and so you can check these out if you're not in class, okay? But let's see this one. Sodium-24 has a half-life of 15 hours. How much sodium-24 will remain in an 18-gram sample after 60 hours? So what we're going to do is we're going to take 60 hours, the total time, and we're going to divide it by the value of a half-life. That's going to give us how many times the sample cut in half. So if I do 60 divided by 15, I get 4. So that means the sample cut in half 4 times. Okay? So what I can do is I can take the original mass of my sample and I could divide it by 2 4 times. And that's what I'm going to get. So I could just do that in my calculator. Now, the way, the more efficient way is, okay, 4 half-lives. That means 1 half times 1 half times 1 half times 1 half. So that's 1 half raised to the 4th power. So 1/16. So 1/16 of the original remains. So if you just do 1/16 times 18, right? 1/16 times 18, that would give you the mass that remains. And so that comes out to be 1.125. But if you just take your calculator, and you can follow along with me, type in 18 and divide it by 2 and hit enter. Okay, so that would represent 1 half-life, and you have 9. Then take 9, divide it by 2, and hit enter. That's 2 half-lives, and you have 4.5. And then you would take 4.5 and divide by 2 and hit enter. That would be 3 half-lives. That comes out to be 2.25. And then if you divide that by 2, that's 4 half-lives, and you have 1.125 grams left remaining. Okay? So these are the types of questions you might see. And what might help you, and this is also posted in Schoology, are the half-life equations. You don't need equations to answer the half-life questions that you will see in this course. But if you like equations, if you like plugging in and solving for them, here's a list of equations. Just when you look at this sheet, this should be, this n is an exponent, so it should be 1/2 raised to the nth power. And same thing here, this n is an exponent, 1/2 raised to the nth power, okay? But you can check out these half-life equations and see if they make sense to you, all right? But as long as you can look at a graph and figure out what the half-life is, and so again, I'll show you an example of that. So here's a graph, and they ask you to figure out the half-life. Well, if you start with 600, what's half of that? 300. How much time did it take? 60 days. So the half-life of this isotope is 60 days. And you can see after another 60 days, 60 to 120, after another 60 days, it cuts in half again, 300 to 150. And after another 60 days, it cuts in half again. So the half-life of this isotope is 60 days. So as long as you can do stuff like that and answer questions like this one, okay, you should be in really good shape and have a good understanding of what half-life is, okay? So thanks for listening, and have a great day.